Reactions with multiple steps. So here we'll be explaining why using stoichiometric coefficients is not the most accurate method for determining rate laws, determining rate-limiting steps within reactions, and probably the more accurate way to talk about this is to say using what I tell you is the rate-limiting step in various ways. We'll define intermediates and identify them in a reaction mechanism, and then we'll use a mechanism to write a more accurate version of a rate law based on the rate-limiting step. This last outcome is actually going to be kind of two parts. We'll cover part of it here and part of it in the next video. We'll do the simple version here, and it gets a little bit more complex and we'll need it later. So let's first talk about two different reasons why we need to look at the mechanism when we're talking about rate laws. Now, the first is just an issue that comes up in general, not specifically with multiple step reactions, although it comes into play here too. And that is that if you have two reacting species, it's possible that they will only react if in a very particular order. So if you look at this top list, or this top picture, perhaps that causes a reaction to occur. But if you look at the bottom one, perhaps no reaction occurs. And this is going to be a big deal in all of our reactions that we deal with. So these orientations definitely matter. Now, what we're going to cover a lot in this video is this idea that multiple steps also matter. So if we have three reactants and they go to a product, so here I have A, B, and D being our reactants, E being our product. This may not all occur in one step. And actually, if you have three reactants, likely it's not going to occur in one step. Usually a three reactant system will occur in more than one. So maybe instead you actually have A plus B going to some other species C. But then that species that A and B makes, that C, it is going to react with D to form our final product. And so if you look at the overall reaction, it looks like you just have these three initial reactants forming a product. But there's also these in-between steps. When we're looking at these multiple step reactions, oftentimes they aren't the same speed. Maybe step one is really, really slow. A and B just don't really want to react for whatever reason. But once they do, the second reaction is really fast. That's going to change how our rate law acts. And let's think about why. So for this, we'll use a little analogy to think about it. So at Summer Olympics not too long ago, we had a relay team, and they won the gold medal, broke the world record. So they were really fast. Their world record was 36.84 seconds for a 4x100. Now, let's look at what happens if just one of them, so world record holding team, just one of them gets sick, and he can't participate in the relay race anymore. But it's okay because they found a fill-in. So we're going to have our pop sensation Justin Bieber fill in for this. So now they run their race. And even though three of them, world record holdings, their new time is 59 seconds. And for those of you who are not super familiar with times of a 4x100 relay race, that's actually way slower than most high school teams can do. So we took a world record holding team and we put in just one switch, one slow person, and now we're worse than high school teams. So why is this? Well, the slowest step is always going to be what we call rate limiting. It doesn't matter how fast the other ones are if our really, really slow step holds everything back. Now you might say, well, what's slow and what's fast? Give me a number here. Well, we can't really do that because it just depends. So let's take this example again. But now 3 of them get sick. 3 of them can't run the relay race anymore. But we decided Justin Bieber's out, no more pop sensations in the relay races. Now we're going to bring in DC's finest. And they're going to take over for us. So we look at the new time, and our first nice, really fast by human standards Olympic medal holder runs his 9.1 seconds. But the superheroes now are so much faster that really they hardly took up any time. They're sitting there waiting around for one of our fastest humans to handle the situation. and then it's pretty much done with. So slow and fast here are very much relative. It's slow as compared to the other steps, fast as compared to the other steps. So why would these multiple steps matter? So let's look at our initial example again. We have our slow step going first, and then we have our fast step going second. And let's write our rate law based on this. We'll use our stoichiometric coefficients. Here. Now, if you wrote this based on the whole reaction, if you used A and B and D, it wouldn't look the same as this. But here's the thing, the amount of D doesn't matter so much as long as we have enough, as long as we have some, because that reaction is going to happen so much faster than the first step. So A and B take forever to react, forever in terms of this reaction. And then the second we get C, our D uses it up quickly. Again, all in terms of relative to each other. So now let's talk about something else that happens here. And this becomes really important when writing rate laws, and so I stuck the definition in this video. And that's something called intermediates. Intermediates are not present in the final reaction. But there's going to be another thing that we talk about later on that's true for too. So there's something else we need to add in here. It is formed during the reaction. In other words, we don't add it in. We don't, pull out a jar of an intermediate and sprinkle it into our reaction. The reaction itself forms it. But it's not a product because then the reaction uses it back up again. So the reaction forms it, and then as part of the next step, or maybe even the next step, it uses it back up. So let's look at our example that we've been using. What is the intermediate here? So take a second and look at what species, and I kept it really general, what species here is formed as a part of the reaction, used up as a part of the reaction, and therefore is not written in the final equation. So you see that in the first part, we have A plus B goes to C, but then C gets used back up again. And so here, C is our intermediate. Now, something that's very, very important is that your intermediate never be in your rate law. You're not allowed to have that happen. And I set this example up specifically so that it wouldn't happen for us, so that we could talk about it. If you look here, we have A and B, and we wrote this rate law based on our slow reaction, because that's what slows the reaction down. That's the rate limiting step. And there was no intermediate there, and so this wasn't a problem. If it is a problem, if you do have an intermediate in your rate law, we have to fix that. And we'll talk about that in following videos. So quick review. Stoichiometric coefficients are not generally your best way to go about determining a rate law. However, this gets a lot better if you have a mechanism. Because if you have a mechanism and you know what is your slow step and what is your fast step, you can now base your rate law on your rate limiting step. And that's going to get you closer to the right answer. It may still not be perfect, but it'll be closer. You can never have an intermediate in a rate limiting You can never have an intermediate in a rate law. We talked about how to write them for equations where that's not a problem. And in later videos, we'll figure out, well, what happens if you do end up with an intermediate in your rate law? What can you do about that? How can you remove it so that we don't violate this rule?